Your standard RAG prototype flawlessly. You embed a few thousand documents, run a query, and the system instantly returns highly accurate context. This creates a false sense of security, because when that exact same architecture hits production data volumes, the underlying logic begins to break. The baseline mechanic of standard vector databases is the bottleneck. At query time, the system computes cosine similarity against every single stored vector in a flat index to find the closest match. With 10,000 points, that calculation takes milliseconds. With 1 billion points, computing that distance for every single query becomes a hard mathematical limit. As you scale high-dimensional data, the curse of dimensionality kicks in. At 1,536 dimensions, the mathematical distances between individual embeddings become uniform. The distinct clusters of meaning dissolve, and everything starts looking equally close to everything else. This chart illustrates the latency precision paradox. As your data volume grows, your retrieval accuracy collapses while your processing time spikes. Your system will often return results quickly under heavy load, but those results are mathematically random, which directly causes your LLM to hallucinate answers based on garbage context. This is compounded by enterprise metadata. Standard flat indices execute semantic retrieval first and filter for tenant metadata second. The system computes similarity across millions of vectors, only to throw the vast majority away because they don't match the required user or date filters. Horizontal scaling of compute cannot resolve a mathematical decay in retrieval precision. Pushing RAG to this scale requires an architecture that moves beyond simple vector similarity to address the specific bottlenecks of dimensionality and metadata filtering. If you are building a SaaS product, your architecture must reliably host thousands of separate clients on the exact same underlying RAG infrastructure. Logical isolation stores all vectors together, causing the noisy neighbor problem, where one client's heavy batch job degrades latency for everyone. The solution is tiered multi-tenancy. Enterprise clients get physically isolated, dedicated shards, while smaller clients share efficient logical resource pools. But isolating data introduces a severe security flaw. If a system retrieves semantic matches first and checks permissions second, query latency exposes restricted documents. To close this gap, you implement vector-level role-based access control. This embeds the security check inside the retrieval pipeline, ensuring the system only computes similarity against authorized documents. Running authentication prior to retrieval operates as a mandatory InfoSec barrier and a critical compute preservation mechanism, ensuring you never waste CPU cycles. Dense vectors capture broad semantic intent effortlessly, but they routinely miss exact literal tokens. If a user queries a highly specific alphanumeric server error code, dense retrieval will often return generic troubleshooting guides instead of the exact technical document. Exact precision requires a dual-lane retrieval architecture. The query is processed simultaneously through a BM25 sparse search for keyword matches and a dense vector search for semantic meaning. Because BM25 scores and vector similarities use different mathematical scales, averaging them corrupts data. Instead, use Reciprocal Rank Fusion. RRF ignores raw scores, merging lists strictly by rank position. A document ranked highly by both algorithms is pushed to the top. The RRF pipeline guarantees the correct document is retrieved, but bioencoders lack precision to rank it absolute first. For absolute precision, the top 100 RRF candidates pass to a cross-encoder, which processes query and document tokens simultaneously to radically reorder the final top 10. State-of-the-art enterprise search relies on this multi-stage fusion of lexical matching, broad semantic retrieval, and deep token interaction re-ranking. Serving these results with sub-millisecond latency introduces a severe hardware constraint. Storing 1 billion raw 1,536 dimensional vectors as 32-bit floats requires 6 terabytes of RAM. You bypass this memory wall through product quantization. PQ slices each high-dimensional vector into subgroups, clusters them, and stores a simple codebook ID instead of raw float values. This achieves a 64:1 compression ratio, dropping RAM requirements from terabytes to gigabytes. Aggressive quantization reduces search accuracy. You offset this loss by mapping the compressed vectors onto an HNSW graph. Queries travel across sparse upper layers to traverse vast distances instantly before dropping into the dense base layer to locate the precise nearest neighbor. You further optimize memory by partitioning the index temporally. Older, inactive documents remain on disk, ensuring only highly relevant data consumes your active RAM. Operating at billion scale requires engineering a deliberate balance between destructive data compression and highly optimized hierarchical routing. Once deployed, production RAG systems rarely suffer sudden, catastrophic mechanical failures. Instead, they degrade quietly and invisibly over time. This graph tracks retrieval quality over 6 months. As user queries evolve, new terminology is introduced, and business data shifts, the static embedding model slowly loses semantic context. This phenomenon is known as embedding drift. Mitigating this requires automated continuous evaluation pipelines. You must regularly test your active index against verified golden datasets to track recall rates and detect drift. When the drift requires migrating to a newer embedding model, re-embedding 50 million documents takes massive compute and risks days of system downtime. The zero downtime solution is shadow indexing. You construct the upgraded index in the background while the original serves all queries. Once evaluated, you execute a gradual traffic shift, routing queries from 5. Highly active data is kept hot in RAM. Warm operational data is mapped to SSDs, and cold archives are pushed to cheap object storage. On top of this, documents are compressed via product quantization, structured for fast traversal through an HNSW graph, and locked securely inside physically isolated multi-tenant shards. When a query enters, it drops through the vector-level security authorization, splits into the sparse and dense dual-lane processing pipeline, fuses mathematically via RRF, and undergoes strict token interaction re-ranking before reaching the LLM. Enterprise-scale information retrieval exists as an aggressively maintained operational state, continuously evolving alongside the massive data it serves. And optimizing this retrieval layer is only the foundation. The next step is connecting this precisely tuned vector data to a knowledge graph, enabling agentic models to perform complex multi-hop reasoning.